everyone to this final part in the Light Bite series on creative lighting design. In this part we will talk about glare. It will be presented to you by Gilles Vissenberg, functional owner of the illumination optics at Philips Lighting.
Welcome to this Light Bite about discomfort glare. In this presentation I will discuss the different glare measures that have been used to evaluate the discomfort glare in a lighting installation and the research that has been done to test whether these are still valid for modern luminaires. If you look at the human visual system, it is capable to adapt to brightness levels that are very low, like on a starry night without moonlight, but also to light levels that are very high, like during a sunny day. Well, it does so in three different ways. The first way to control the amount of light that enters the eye is to vary the size of the pupil. This can be done really fast, about a second response time is needed. And this way we can change the light level with a factor of about 10. For this reason, an ergonomic lighting design for interiors uses often the rule of thumb that the brightness should be within a factor of 10 variation. This way we can ensure that the lit environment is very comfortable to look at. But we can vary more than a factor of 10. To vary about a factor of 100 to 1000, we have neural adaptation. So the signals that are received at the retina are transmitted to the visual cortex by neurons, and the weights that they give them can vary very quickly in about 200 milliseconds. And these two mechanisms are used for most common variations of light levels for indoor lighting. Well, like said, outdoor the variations are more extreme, so a sunny day to a dark night is much more than the factor of 1000 we can gain with neural adaptation. For that we have photochemical reaction in the photoreceptors of our retina. This can easily be more than a factor of 1000 variation in brightness adaptation, but this is slow. It takes several minutes, up to half an hour. Well, if you are adapted to a certain level of brightness and you are confronted with a light source that is much brighter than the adaptation level, then we speak about glare. So the glare can be completely blinding, which happens when you look into the sun, for example, then you see nothing at all for a short period of time. When the vision is only partially impaired, we speak about disability glare. And of course, this can be very dangerous if you talk about traffic. It's an important topic for outdoor lighting. In interior lighting, disability glare can occur, but then it's usually because of daylight that enters through the window. From the artificial lighting installation, discomfort glare is the most important aspect. We speak about discomfort glare when people are not impaired in their visual task. They can see everything they need to see, but the light source is still irritating. People want to look away. It causes stress or fatigue or headaches, for example. But the problem with discomfort glare is that it cannot be measured directly. So we can only ask people about the comfort they experience in the lighting installation. Nevertheless, there have been several methods described to give a rating to the discomfort glare level of a lighting installation. I just give a few examples. For indoor lighting, there were many ways to determine discomfort glare. But after about 20 years of heated debates in the CIE, the unified glare rating was determined in 1995. And this unified glare rating is used for interior lighting in most countries in the world. What it does actually, I will not explain the formula in detail, but what it does is it looks at the luminance of all the sources that you can see when you sit in an office, for example, and it adds up the luminance values of all those sources in a certain way. And well, many people know the number UGR19, which is the limiting value for office task lighting in many countries. In outdoor lighting, we unfortunately don't have such a consensus on discomfort glare. I'll just give one example. The North American IESNA has a so-called tolerable cumulative brightness effect. It is more or less similar to UGR in the sense that it adds up the luminance values of all the bright sources that are in your field of view. Another source of glare can be reflected glare or indirect glare. So when you see the reflection of a source in the screen, for example, of a monitor or on a glossy paper or on a glossy surface somewhere. The European norm for that, the EN 12464-1, describes a limiting value of the luminance at angles larger than 65 degrees. And so there are more ways to give a rating to the discomfort glare, but the important observation is that all these discomfort glare ratings use the average luminance of the glare source. Well, the average luminance of the glare source is nothing more than the intensity of a source divided by the emitting area. But as you can see from the examples I give here, these are quite common troffers used for interior lighting, but it's not very trivial to determine the luminous exit window. So where do you stop? And you can imagine if you don't take the right area, you get the wrong luminance value. And it becomes even more complicated if you talk about LED luminaires, because there are many products out there which have visible LEDs. And how do we determine the average luminance of an array of LEDs? Well, we are not the only ones observing this, especially in Japan, because of energy saving. A lot of offers were introduced with LED matrices that were visible. And also a lot of complaints came from the market that people say, okay, the UGR value may be good, but it's still not very comfortable to work under these lightings. So a lot of studies have started, so like I said, first in Japan, but now later also in Europe and also in the United States. Research has been done of people sitting in a space and then showing them luminaires with different spatial distributions of the luminance and then asking them about the comfort level. At Philips, we have also done studies like that. So what you see here in the top right is a picture of an office space at the high-tech campus in Eindhoven. And we equipped that space with special luminaires in which we can control the luminance distribution of the exit window, but we can keep the lighting distribution in the room constant. So we only change the appearance of the luminaire, but the amount of light and the distribution of the light coming out is constant. In our first test, we varied the concentration of light in the center. So we could evenly distribute all the flux and all the luminance over the whole area, which is the left picture, and then increasingly have more light in the center part. And we found that the three pictures with the blue rim around it, they all give the same perceived glare. So it doesn't really matter in this experiment how the luminance was distributed. They all give the same glare. Only the one on the right, where all the light was concentrated in the center, was perceived as more glary, but that's what we expect because the source is smaller and the average luminance is higher then. So that can be predicted with UGR. No problems there. In a second test, this center was split up into small dots. So we varied from a uniform source on the left to an array of very bright dots with a very dark area in between them on the right. And we found out we could go very far. So the two pictures on the left were perceived as being equally glary. But if you go to really extreme contrast levels and really extreme peak brightnesses, then the glare is higher than predicted by UGR. Because these three examples, the area does not change, the flux does not change, the intensity does not change. So according to UGR, they should all have the same glare. This test was repeated, so we did not only do it in Eindhoven, but also in the USA, in Briarcliff, and also in Shanghai, in China. And actually we found more or less the same results. So if you go from the total area lit to only the light concentrated in the center, there's a step in acceptance. So less people accept the lighting conditions as being comfortable. And if you split up the center part into small dots, then even less people will accept this as being comfortable lighting conditions. So the conclusion of all these three studies is that for the global variations of light, so when we concentrate the light in the center or not, UGR is quite a good predictor, not different than what we are used to. But if we go to an array of very bright dots with a high contrast, then UGR is underestimating the glare. In Eindhoven, also tests have been performed on outdoor luminaire conditions. So It's a very low light level compared to the test we did in the office. And very bright arrays of LEDs were put on a pole at a large distance. And the outcome of this test, let's go to the outcome, is if people were asked not to look into the luminaire but just look straight ahead in the direction of the luminaire, then the average luminance is still a good glare predictor. So we don't need the details of the luminance distribution to predict glare. But if people are asked to look into the luminaire, they can distinguish the details, and then it does make a difference how the bright sources are distributed. So based on the increasing amount of evidence that something has to be done, CIE started a committee to review the literature on glare of non-uniform sources, and also to come up with a correction for the UGR. We have to find out for which luminaires is UGR no longer valid, and how should we correct. Well, to do so, we have reviewed all the literature. We've reviewed 60 papers, starting from 1974 until this year, but most of them were of the last 2 years, because it's a very prominent topic only of the last 2 years, when LED luminaires have entered the market and started leading to complaints. Those 60 papers refer to 43 studies comparing uniform and non-uniform luminaires, and these different groups, they propose 19 different ways to predict discomfort glare. Of these 19 alternative ways to predict discomfort glare, about 13 proposals were made to give a simple modification of UGR. And luckily, we are down now to 2 main directions of thinking. One of them, if you look at the formula of UGR, one of them is to have a different way to calculate the average luminance by using a luminance image of the source. And the other one is by calculating the luminous source size in a more precise way than is done now. And in fact, I think many people in the committee already agree that those 2 approaches can be merged into one, but we are still in the process of seeking consensus on a single approach. So, to summarize, there are several ratings used out there to find out the discomfort glare of a lighting installation, but they all use the average luminance of the source. Based on complaints, people have started to research that, and luckily it has been found that the perceived glare of uniform and non-uniform sources is often the same. So in many cases we can still use the current glare ratings, but we have to be careful with luminaires that have an extreme contrast between bright and dark parts. For example, the bare LED matrix luminaires that are sometimes used. But that's not enough, because if these luminaires are placed at a high ceiling, like in an industry hall, or at a very high pole, then people don't look into it, and then it also doesn't make a difference. So for a very high contrast luminaire that is close to the line of sight, then we have to be careful. And at the moment, CIE is working on a proposal to correct UGR, and we hope to start a new committee to do the same for other glare metrics in the future. Finally, I would like to stress that, of course, glare is a bad thing, and very harsh differences in brightness should be avoided, and especially at people have to do in places where people have to do a demanding task, like in offices or in schools or in hospitals. There the light distribution is even, and we should not even notice the luminaire. But of course, there are many situations that are very different, like in a museum or in a hotel or in a store. You want to attract attention, and then having accents, having contrast, or having sparkle and extreme brightness can be a good thing. So we should not forget about that, but that is a topic of another light bite. Thank you very much for your attention.